Hi guys, today we're going to talk about some neat math tricks that come up a lot or I thought are cool and they're useful to know. So hopefully when you run into a problem that involves one of these tricks, you'll be able to solve it. So let's get started. First one, this is the simplest, we're going simplest to hardest in terms of mathematics, is the trick that lets you write any repeating decimal as a fraction. So consider this decimal, 0.25 repeating, right? That's 25 over 99. How do I know that? Well, I use this formula. For an x smaller than 1, 1 over 1 minus x is equal to this sum of powers of x. And 25 over 99, that's equal to saying 0.25 over 0.299, right? 0.25, divided by 100 top and the bottom. And this 0.99 is 1 minus 0.01. So using this formula here, which x does satisfy as 0.01, it's much smaller than 1. So then you get 0.251 plus 0.01 plus 0.001 plus so on and so forth. What you see is if you multiply 0.25 into this, the first term will give you 0.25. The next term will give you 0.0025. So the 25 here, the 25 here, they won't interfere. This one will just get tacked on at the end. Now keep going on and on and on. You'll get 0.25 repeating. And if you have something that's like 0.257 repeating, all you need to do is make this a 0.001. So that would be 257 over 999. 257 over 999. And I guess that is simplest terms. Okay, probably. All right. So what if you have a fraction that looks like just one digit repeating, right? So 0.25 repeating in this case. So, well, 0.05 repeating. This one is what? This is a tenth of 5 nines, because 5 nines, this is the same trick with one digit, right? 1 minus 0.1. So that'd be repeating every single digit, 0.5 repeating, right? But that's a tenth of this because there's an extra 0 in front, which is taken up by this 2. So this here is 1/10 times 5 nines. And this term here, 0.2, is just 2/10 or 1/5. And you just put them in simplest terms, common denominator, add them together. 23 over 90 is 0.25 repeating with just the 5 repeating. So that's how you can write any repeating decimal as a fraction. So how do you factor a sum of two polynomials of the same degree? So for example, if you have x minus 5 to the fourth plus x minus 7 to the fourth is equal to 20, or minus 20 over here if you like, same thing. How do I solve this equation? Well, you want to expand it, but if this was a quadratic, you could do that. It would be cool, but this doesn't simplify things because you still don't know how to solve a general quartic and nothing really happens here when you expand it. I mean, you can plug it into a calculator, but we're assuming you don't have a calculator for this. You can actually solve this by hand. So what you do is you use substitution u equals to x minus 6. And you're going to get u minus 1 to the fourth and u plus 1 to the fourth. And that's going to be equal to 20 still. And what happens here is when you FOIL this out, first term u fourth, second term minus 4 u cubed, right? First two terms of this one, u fourth, and this one's going to be plus 4u to the third. And what you see is when you add these together, the even power terms combine, and you get them doubled, but the odd power terms, they will cancel, because this negative 1, this plus 1 will cancel. And so this is a really neat trick. What you get is this biquadratic, and I call it that because if you substitute, sorry, this is a u, if you substitute y equals to u squared, then you can just have a quadratic equation here. You'll have y squared plus 6y plus 1 equals to 10, which you can solve. Quadratic formula, back substitute in for y and then u, and then you have your solution. And of course, these don't have to be 5 and 7. Any two numbers you have in here, you can just plug in the midpoint. And this technique will work. It might just be a little bit more difficult to factor the ensuing quadratic. And so this is really neat because if you have even, say, an 8th degree polynomial, which in general an 8th degree polynomial is not solvable by a calculator, right? But if you can write it in this form, then you can solve it in this way, because what you'll get out is a quartic. And a quartic in general is solvable by a calculator. They are generally factorable. There's a very long formula, but you can do it. So this will tell you if you can write something this way, whether an 8th degree polynomial is factorable or not. It doesn't work for 10th degree because calculators can't in general solve 10th degree polynomials, but you know, it is what it is. It's still pretty useful and definitely neat. So the next one is pretty simple. It's a change of base formula. Here's just the mnemonic. You should know, probably from precalc, that log A of B is log B over log A. But I always get confused which one goes on top, which one goes on the bottom. Easy way to remember this, log 2 of 4 is 2. So log 4 is 2 log of 2. So that way you know that log 4 is on top when you're writing it this way. And here's another useful thing you can see. Log 2 of V is ln of V over ln of 2. E is 2 to the 1 over ln of 2. And this is interesting because it lets you estimate E if you can estimate ln of 2, which is something that can be useful, for example, if you're trying to do a Monte Carlo approximation. But more on that later in a different video. So continuing, let's go to the roots of unity filter. This one's a little bit more niche, but it's a pretty cool trick, so I thought I'd bring it up. So suppose that I want to sum combinations that look like this. So n goes up to 1,000. 1,000 choose 2n. So 1,000 choose 2, 1,000 choose 4, 1,000 choose 6, so on and so forth. What's this sum, right? And the answer is, if this was a, not a 2n, but just an n, these would just be binomial coefficients, right? There'd be just, like if this is x to the n here, then this is 1 plus x to the 1,000th power, right? And you can pretend like the x here is just a 1, so that'd be 1 plus 1 to the 1,000, it'd be 2 to the 1,000th power if there was no 2 here. But there is a 2 here, so what do we do about that? Because we don't have the 1,000 choose 1, don't have the 1,000 choose 3, so on and so forth. Well, the answer is that we can rewrite this. So instead of eliminating straight up the odd terms from this sum, we can use this function to eliminate them for us and have a normal sum here. So let's see how this works. So 1 to the n plus negative 1 to the n. If n is even, then this will be 2. If n is odd, this will be 0. So you see we still only keep the even terms in terms of this n. The 1/2 cancels the 2 you get here. So why is this useful? Well, using this expression here, we can put this negative 1 here. We say this is 1 minus 1,000. This is 1 minus 1 to the 1,000th power. 0 to the 1,000th power, this term. That's just 0. But this term is 1 plus 1 to the 1,000th power. So that's 2 to the 1,000 over 2. This is 2 to the 999. 999. And now we evaluate it as a binomial. And you can do this for any multiples of n, so like 3n, 5n, whatever, using the sum of e to the I pi over n's. So for example, if this was every 3n, you would do 1 plus e to the I pi over 3 plus e to the 2 I pi over 3. And that would give you the same result. Yep. So, no, sorry, that's not quite right. You want to do you want to do 1, you want to do e to the 2 I pi over 3 and e to the 4 I pi over 3. You want them to be evenly spaced around the unit circle. So e to the 2 I pi over n, this should say. My bad. And this actually can be used if you want to evaluate. This is an interesting trick as well, because even if you have an n here or a 2n or something, you can evaluate this because we said, well, suppose you have this, right? This is 1 plus x to the 1,000th for x equals to 1, right? 0, 0. And if you have this x to the n in here, well, now this is just x the derivative, x to the n minus 1, and you bring up everything by 1. So this is the derivative of this. You can evaluate it as such because you know what the derivative of this function that's equal to is. So this is a pretty useful thing in general. It's a little bit niche, but there it is. Next one is the Leibniz Rule. So suppose you have a bunch of energies, an energy spectrum, right? A bunch of energies, EI. And you want to evaluate the expectation of these energies. Which energy is the most likely, or maybe something in the middle. Well, in general, you would do a sum of EI to the PI. And usually in statistical mechanics, which is where this comes from, PI can be written as e to the negative beta EI. Beta here is a constant. It's equal to KT, 1 over KT. So e to the negative beta EI is PI in thermodynamics usually. And the sum of all the probabilities, which should be 1, is called the partition function. It may or may not be normalized. In general, it's not. But we're going to pretend like it is for now. So we want to find this expectation of E. How do we do it? Well, the answer is, we notice, because we could just put an EI here, but we wouldn't necessarily know how to sum this. We notice that taking a dd beta, will drop down these factors of EI, and also drop down a negative, but not a huge deal. So what we notice is that dz d beta is going to be negative expectation of E. In general, if z is not normalized, it should be d of ln of z d beta. So you get the normalization factor of z on the bottom. But we're not going to worry about that for now. And the point is, this is very useful for finding expectations of many things. So for example, if you have a magnetic field, so a Zeeman effect, right? Zeeman effect. So the energy is maybe equal to mu b or something like that. You have a Zeeman splitting. Not Zeeman splitting, just the magnetic field polarizations. And your energy is equal to mu ib, and you want to find the expectation of mu. Well, then you take d db. This will drop down a factor of beta. This will drop down a factor of mu I that you want. So just multiply the beta 1 over beta to cancel out the factor of beta that you get, and you'll have sum of mu I pi, and that will give you the expectation of mu. So this is a very useful technique for finding expectations of things, and it's the same technique that allows us to do Feynman's trick, just in a discretized form. Next one is a tan x over 2 substitution. Very straightforward. Want to integrate our rational trig function to do the substitution. Gives us these very nice properties of what sine, cosine, and dx are. And you'll see in this example, 1 over 3 plus cosine of x. 3 plus 4 cosine of x. How do you integrate that? Well, just plug these in, plug and chug. And what you see is this 1 plus u squared will cancel. It makes these terms combine nicely, and we get 1 over 7 minus u squared, which you can do by partial fractions. Very tractable. So the last one I want to talk about, very useful, the gamma function integral. It's really simple. This is the only thing you need to know. This integral is equal to n factorial. So it's very common that you have to do an integral like this in quantum mechanics, because you'll often have like a Stark effect, electric field between two eigenstates of the hydrogen atom, and you want to evaluate what the dipole moment is. So that comes in as a factor of x, and this is what the hydrogen wave functions look like in the first place. So if you want to evaluate the dipole moment, you often have to do integrals like this. And if you want to do this, you just have to do the substitution u equals to ax, pick up n plus 1 factors of a, and it's done. And this is the last trick that I want to talk about. Video's over. Hope you guys enjoyed it, and see y'all later.